Welcome, and thank you for attending our presentation online due to COVID-19. My name is Preston Sanderson,
And I am Kaushik Shah.
and we did research with our professors Pablo Garcia Fuentes and Joseph Smalley, forecasting of the S&P 500 index in the Dillard College of Business Administration for the Financial Management Association's Forecast Competition Celebration of Scholarship, Spring of 2020. The S&P 500 is a stock index that tracks the stocks of 500 large-cap U.S. companies. It represents the stock market's performance by reporting the risk and return of the biggest companies, making it a good indicator of the U.S. economy. Investors use the S&P 500 as a benchmark of the overall market to which all other investments are compared. In this research, we focus on forecasting the monthly average price of the S&P 500 index. The data we are using covers the period from January 2000 to 2019. The objective of this research is to forecast the price of the S&P 500 index using ARIMA, Autoregressive Integrated Moving Average forecasting method. The data period is January 2000 to December 2019. The autoregressive integrated moving average ARIMA procedure is used to analyze and forecast the S&P 500. The method allows for predicting the future values of the S&P 500 based on the combination of its past values and past errors. We follow the three stages of the ARIMA modeling: identification, estimation, and diagnostic checking, and forecasting, where T is time, B is the backshift operator, is the S&P 500 index, is the moving average parameter, is the autoregressive parameter, and is the independent random error. The plot of the original series gives an idea of the behavior of the series over the period from January 2000 to December 2019. This graph is the plot of the S&P 500 in the original scale. The table below shows the descriptive statistics for the S&P 500. We conduct the identification of the log of the S&P 500 series based on the figure trend and correlation analysis below. The figure below shows that the series has an obvious time trend. The autocorrelation function does not decay as the lag increases, and the PACF shows two significant lags. The ACF and the PACF plots suggest an AR process. In addition, the table autocorrelation check for white noise shows that the p-values for the 36 lags of the series are highly significant. So the white noise hypothesis is rejected, as it is usual for non-stationary series. If you look to the graph on the right, you will see that the IACF shows no overdifferencing. The table below shows the descriptive statistics for the first difference of the series. The figure below shows that the ACF decreases rapidly, which implies that the first difference of the S&P is stationary. The partial ACF and the inverse ACF suggest an AR model. The PACF and the IACF also suggest that there may be some seasonal effects. That is, there are some lags that are non-zero. So we do a 7-day seasonal differencing in the next section. The autocorrelation table below shows that the S&P 500 highly autocorrelated, so an autoregressive of order 1 model AR may be ideal to model this series.
The stationary test of the original series. This section shows the stationary tests. The identification stage in the last slide suggests that we need to difference the S&P 500 series. To test if the series is stationary, we conduct the augmented Dickey-Fuller test ADF, and the Phillips Perron test. The ADF and PP tests are conducted using zero lag differences because the identification test suggests an AR1 model. So the ADF and PP unit root test tables shows the test for zero lags. Because the series has a trend, we use the trend model for the test. Note that the p-value on the tau statistics is more than 5%, so the hypothesis is that the series is non-stationary, is not rejected. Stationary test, first difference of the original series. This section shows the stationary test on the difference series. The ADF and PP tests are conducted using zero lag differences because the identification test suggests an AR1 model. So the ADF and PP unit root test tables shows the test for zero lags. We focus on the trend model for the test. Note that the p-value on the tau statistics is less than 1%, so the hypothesis that the series is non-stationary is rejected by both tests. Therefore, as suggested by the identification stage, we need to difference the series because it is non-stationary, and stationarity is shown in the graph for S&P 500 and the first difference of the series, which means that the series embraces the zero line. Note the difference with the plot of original series. Diagnostics to identify ARIMA models. The identification stage suggested that an ARIMA 112 model, which is a process made up of AR1 and MA2 and a seasonal moving average. To verify that this is the appropriate model for the SP500 index, we conduct identification tests. We use the smallest canonical scan correlation method, the extended sample autocorrelation function, and minimum information criterion tests. The table below shows that the three tests suggest an AR1 and MA1 as indicated by the identification stage, where P is equal to 1 is the order for the autoregressive process, and D is equal to 1 is the level of difference, and Q is equal to 2 is the order for the moving average process. In addition, P plus D is equal to 2, so this suggests that an ARIMA 112 model. Results, the forecast of S&P 500. This section shows the results of the forecast of S&P 500 using ARIMA 112 and 1127 model. The selection of this model was based on the tests we did above in the earlier slides. The conditional least square estimation shows that ARIMA model parameters estimates are significant at the 1% level. The p-values are less than 0.01. The residual diagnostic is acceptable. The residuals approach normality as suggested by the residual normality diagnostic figure. So the estimated seasonal ARIMA 1127 model for the SP500 is mentioned in the slide, where T is equal to time, B is the backshift operator, and ET is the independent random variable. This graph shows the forecast of S&P 500. The line in straight blue line is the actual values of S&P 500 from January 2020 to April 2020, and the dotted points are the forecasted value. As you can see, the forecasted value moved very closely along the actual values, and this shows that our forecast is very accurate. And as you can see, the confidence limit is 95%. This table here shows the forecasted values of S&P 500 index from last Friday, that is 4/17, and it goes on until May 6th. In this slide, you can see the forecasted value of the S&P 500 index from our model compared to the actual value of S&P 500 on Friday. So the forecasted value from our model is 2,745, whereas the actual value was 2,874, showing that there's our forecasted value is down by 4.75%. This is still a good forecasted model because our model does not take into consideration the coronavirus pandemic. Conclusion. So in this forecast of S&P 500, we used ARIMA 112 and 1127 model to forecast the index. Based on our model, the S&P 500 index is expected to decrease. However, the model does not take into consideration the effect of coronavirus pandemic. This model uses the past data of the index to forecast the future values, and therefore it is very difficult to take into consideration anomalies like coronavirus. Thank you everyone for watching our video, and I would like to thank our mentors, Dr. Pablo Garcia Fuentes and Dr. Joseph Smalley. And thank you, Eureka, for giving us this opportunity.